Welcome to part 3 of our talk. It's me, Allie, from part 1, and I am back to talk about the composition of exoplanets, and I will be trying to answer the question of what are they like. To start, we will begin with hot Jupiters. Hot Jupiters are gas giant planets with orbital periods of less than 10 days. The short period means that hot Jupiters are very close to their host stars, usually less than 0.1 AU, which is 1/10 of the distance between the Earth and the Sun. So this would be compared to our period, which is the time it takes us to orbit our Sun, of 365 days. So you can get a feel of how short that period of less than 10 days really is. Hot Jupiters dominated planet discoveries for at least 1 decade because they are the easiest to find with the radial velocity technique and the transit method, both of which we talked about in part 1 of the talk. Hot Jupiters have a common temperature of about 7,800 degrees Fahrenheit, so you can see where the name hot comes in. They are gas giants like our own Jupiter, and they commonly have wildly eccentric orbits, which means that they come close to their star and then they swing far away and again come close, creating that very eccentric orbit. So at first, hot Jupiters were considered oddballs since we don't have anything like them in our own solar system. But as more were found, in addition to many other smaller planets that orbit very closely to their stars, our solar system actually started to seem like the real misfit. So here are some examples of hot Jupiters that have been found so far. This is using the wide angle search for planets. That's what this WASP stands for. And you can see how close they come to their star and then how wide they swing out after that close encounter. So the big question that astronomers are trying to figure out is how did they get so close? We don't have anything like this in our own solar system, so this is a very tricky question to answer. So there are 3 categories of models that people have come up with. One is that maybe these planets form close to their stars to begin with. Originally, people sort of dismissed this, but more recently, astronomers have been taking this theory a bit more seriously as more studies and simulations have shown the conditions under which this actually could happen. Another explanation is that during the stage when the planetary system was forming out of a disk of gas and dust, the Jupiter was pulled in closer to its star. The last explanation is that the Jupiter could have started far away from the star and then gotten onto a very elliptical orbit, probably through gravitational interactions with other bodies in the system, so that it passed very close to the host star. It got so close that the star could raise strong tides on the Jupiter, just like the moon raises tides on the Earth. That could shrink and circularize its orbit so that it ended up close to the star in the position that we observe. So this is still a highly debated question, and lots of research is being done to figure out exactly how these hot Jupiters became so close to their star. Next, we will talk about the composition of these exoplanets. Astronomers have come up with 4 types of exoplanets, 4 categories that we put these planets into. We have gas giants. These are the size of Saturn or Jupiter, or they could be much larger. These include the hot Jupiters that we just talked about. Neptune-like planets. These are similar in size to our own Neptune and Uranus, with hydrogen or helium-dominated atmospheres. Terrestrial planets are Earth-sized or smaller, mostly made of rock and metal. And then we have our super-Earths, which are typically terrestrial or rocky, and more massive than Earth, but lighter than Neptune. Not much is known about what exoplanets are made of, but there's a wide range that has been seen so far. So to compare this to our own solar system, our rocky planets are Mercury, Mars, Venus, and Earth. Our gas giants, Jupiter, Saturn, Uranus, and Neptune. Exoplanets have been seen that encompass both the rocky planets along with our gas giants. So a wide range has been found so far, planets similar to our own, but also very different from our own. So that begs the question, how many different types of exoplanets are really out there? Now I'm going to turn it over to Gabe for part 4 of our talk, the long-awaited question of, are these planets habitable?